Hey, welcome guys. Yeah, so today let's talk about the function of several variables. Yeah, so this is my not new series, but like the analysis video. Yeah, so yeah, if you haven't seen my analysis video, then I just finished the chapter 8 of the routine, and I will go to the chapter 9. Yeah, and I will use some basic linear algebra. So, and I don't want to prove it again. So this is my linear algebra list. I will post the link below so that we will use it. Okay. Okay. So now let's yeah. So my goal for this series is to prove the following three theorems. One is uh the the inverse function theorem. Yeah, so this type of theorem is a very lengthy to prove and a little bit difficult. And the implicit function theorem, and also the rank theorem. Okay, and follow the routine chapter 9, and also plus the apostle. Okay. Okay, so and I will use some basic linear algebra so that I will use some basic linear algebra. So I will just give the statement and I will not prove because I think this is a common simple in a linear algebra. Okay, so this video, let me just quickly introduce the linear transformation. Okay, so it should be very easy. Everyone knows about what is a vector space. Just a set V with yeah, I mean 10. Yeah, basically you can do two vector addition, and then there's a field C belongs to F, which you can do the constant multiplication. Details go to my linear algebra section. Okay, and also there's a linear independence. So linear independence such that basically if you have vectors, let's say v1, v2, up to vn, and then we say that these are not linear. All these vectors are linear independent if suppose that we get ci vi I from 1 to let's say n equals to 0, and then we have all of ci equals to 0 for each I. This is called linear independence. Okay, so notice that the zero vectors will not be linear independent in any set. Okay. Also by Zhong's lemma, we know that so I should say that so we can say what is the linear span, right? So basically, we can define a span of v1 up to vn defined to be summation ci vi, and of course each ci belongs to your field. Okay. And then we can define what is the basis. Suppose so basis means that if your vector space V can be written as a span of, let's say, v1, v2 up to vn, and this n is called the dimension. And one can prove that the dimension, v can be written as span of v1, v2 up to vn, and also you need to add a condition that each there are linear independent. And n is called dimension, and you can prove that the dimension is fixed and is invariant. And also there's a theory in the linear algebra that I will not prove it because I already proved, and you can go to my video list. Basically, if your vector space V has dimension, the dimension, let's say R, and then your V is isomorphic to the field to the n. Okay. And also there's a linear transformation. There's a T from V to V, defined to be linear transformation if Tx plus y is Tx plus Ty, and the Tcx is Ctx, where C is the field. Okay, so this is called linear transformation. So in the linear algebra, since we're talking about some algebraic stuff, so usually we will talk about there's a thing called dual. and then you can ask a so-called double dual, ask something like a tensor product or something. But in analysis, in the real analysis, or at least the mathematical analysis, so most of them we're just working with the Euclidean space Rn. So let me just define L, Rn, Rm to be all the linear transformation. Let's say T from Rn to Rm. T is a linear. Okay. Okay. Okay, and also yeah, that's it. And you can easily check that. I mean, this L, R, and Rm is also a vector space. It's a vector space which dimension is just m times n. And then you can actually, this is also algebra because any two of them will become, where any two composition of linear transformation will become linear transformation. Okay, so let me just give a definition, which now is not linear algebra, it's a real analysis. So somebody give you A belongs to R, N and Rm, then you can define a bound, the norm of A. Okay, so the norm of A is defined to be, I think it's the sup for all the AX, where so AX, X become an m-dimensional vector. So I can take the norm of the length of the AX, but for every X, I only care about the unit sphere. Sorry, the length one. So I map all the length one vector to the AX and then take the sup. Okay. Okay, so this is called norm of A. Okay, so obviously the simple results is that your AX for each X will less or equal to the norm, the length of the AX will less or equal to a norm of A times the length of X. Okay, so I use the single two line to express the length of the X, length of the vector in the Rn dimension, and use the double line to represent the norm of the operator or the linear transformation. Okay, also yeah, so this is the fact. Usual, and also you can easily say that suppose if AX less or equal to lambda X for some lambda, then obviously that since it's the sup, right? So you can take the sup, so you can prove this. Okay, so this is the commonly used that we will using. Okay, so now let's go to the theorem. Okay, so theorem says that A is suppose L is from, you get A from a linear transformation Ln from M. Then first, let me just give the proof that so the first thing is that the norm must be less or infinite, less than infinity, and A is uniformly continuous. Uniformly continuous. A. Also B. B says that suppose you given 2 from Rn to Rm, and the C is a field. Say C is R. Then you get the A plus B, the norm less or equal to A norm plus B norm. And also CA norm is defined to be it's obviously the C times A norm. Okay. Okay, C is say that if A belongs to L, R, and Rm, and then say B belongs to L, Rm, Rk. Right. So obviously that if you write B A, then become let's say Rn to the Rk. And we will prove that BA norm will less or equal to B norm times A norm. Okay, so this is the common properties of linear transformation from Rn to Rm. Common properties. Okay, let's go to the proof. Okay, so A so sorry, a what? A is as finite, right? So let's see, let's say one can take E1 up to En to be the standard basis of Rn. So standard basis of Rn, right? So any vector X can be written as a summation Ci from 1 to n. And now, right, and since its length is 1, right? So its length is 1. So that means summation Ci squared I from 1 to n is less or equal to 1. Okay. So let's say Ax is basically CIAEI, right? So which is by the Cauchy-Schwarz inequality. So I get the summation CIAEI. Okay, so since each CI, right? Each CI, so each CI is less or equal to 1, right? So this guy is less or equal to summation AEI. Okay, so but AEI is fixed, right? So this guy is finite because AEI is fixed, just numbers. So A is norm is less or equal less infinity. Okay, and obviously, so we need to prove it's uniform continuous, right? But so uniform continuous means that if X and Y are small enough, then AX minus AY should be small enough, right? But now norm is finite, so AX minus AY, AX minus AY, the length is less or equal to the norm AX minus Y, right? So if X and minus Y is small enough, then this guy is small enough. Okay. Now let's go to this proof. So I think this is trivial. So just prove by yourself because you times a constant, which you take absolute value and take sup. So sup will commute with that constant. Okay, now also this one, let me just quickly give the proof. Okay, so this is also simple. You can add a plus bx, take the absolute value. So absolute value already have the triangular inequality, right? So this is S equal to ax plus bx, and by definition, this is S equal to a. Yeah, right, because this is sup. Okay, so now what? Now you just take all the take sup. Right, so this guy, if you've restricted x to be the unit vector, then this guy become a plus b norm, less or equal to a norm plus b norm. Right, so you can restrict yourself for all the vector which is length 1. Okay, then you get this. And yeah, so from this, right, then you can easily show that if I define a distance of two vectors, two linear transformation A B defined to be A minus B norm, then D will make LRN be a metric space. Okay, so I think for this part only the triangular inequality is not obviously. So let's quickly give the proof. Okay, so but now since we already have this, right? So I think it's very easy. Oh, let's consider if A minus C it's just A minus B plus B minus C, right? So by the previous lemma, which is A minus B plus B minus C. Okay, so triangular inequality is true. So one can just, yeah, this is the metric space. Okay, so let's go to the final fact. C is what? C is that BA norm is less or equal to B norm times A norm, right? So this guy is also simple. Yeah, so BAX absolute value is just BAX, right? Because right, common sense. Okay, so absolute value, and by definition, this is a B, right? Because B norm, right, is AX length. And I use another fact. I use another second times, right? So remember that AX is less or equal to A norm times X for any X belongs to the vector space. So I use a second times, which is a B norm, A norm, X, right? So I have this, I have this. And by the previous definition that I always use is the A as absolute value as equal to lambda x for some lambda and A known as equal to lambda. So our BA norm less or equal to B norm, A norm. Okay. And yeah, so next time we will give the lemma, which is very, very important that so that we can prepare all the things to prove the inverse function theorem. And we need to talk about differentiation and also lots of things and the contraction principles. I think we should prepare 3 or 4 lemmas so that we just directly go into the inverse function theorem and use all the lemma and then we prove it. Okay, that's it. See you guys next videos.